Hello and welcome. In today's video, we're going to be going over hyperbolic functions and their derivatives. So to start out, I need to show you two graphs here, and you may recognize both of these graphs. Some of you may not. However, all you need to really know here is this left graph is the unit circle, and this right graph is the unit hyperbola. And as we'll see, these two graphs are the basis of two very similar categories of functions. So, you may recall that this circle has a radius of 1. And similarly, this hyperbola has a distance from the origin of 1. At least where it starts. Then you may recall that if we have an angle theta within this circle, we can find the x value and the y value of any point on the circle, corresponding to the theta, which is just going to be cosine of theta, which is our x, and sine of theta is our y. What we're going to find out in this video is that very similarly, there is going to be a point on corresponding to an angle theta on this hyperbola that corresponds to a certain x value and a certain y value of said hyperbola. Alright, so let's just dig a bit deeper into this. So, certain combinations of the exponential functions e to the x and e to the negative x arise very frequently in mathematics. That they deserve special names. In many ways, they are very similar to trig functions, and have a relationship with the hyperbola, just like the trig functions, as mentioned, have the relationship to the unit circle. As thus, we call these exponential functions, or these special exponential functions, the hyperbolic functions. And they are as follows. Their sine of h is equal to e to the x minus e to the negative x. And I'll just let you look through them all. I'm not going to go through them. But there they are. So, we want to find the numerical values of the following. So if we have sine of h of 0, all we have to do is say that this is going to be the same thing as e to the power of 0 minus e to the power of negative 0 all over 2. This is 1 minus 1 over 2, or 0, for our answer. What about this tangent of x? Well, we know that the numerator here is going to be e to the 0 minus e to the negative 0, and the denominator is going to be e to the 0 plus e to the negative 0. So we get the answer of 0 over 2, or 0. Oh, wait, sorry. I realized that we're not evaluating this at 0. We're evaluating this at 1. My mistake. Bit more practice, though. So we get e to the 1 minus e to the negative 1 all over e to the 1 plus e to the 1. So what we get is 2e in the denominator. And in the numerator, what we get is e squared minus 1 over e. Let's multiply the denominator and the numerator by e. So what we get is e squared minus 1 all over 2e squared for our answer. Alright. for the secant of h, the hyperbolic secant, whenever you see an h, it's read as like the hyperbolic of said trig function. So it's the hyperbolic secant of 0. We get an answer of 2 divided by e to the 0. And I realized that I accidentally wrote this a small bit wrong. It should be a plus. There we go. Plus e to the negative 0. So we get 2 over 2, or the answer of 1. And that is our answer. All right. Now time for some trig identities. So, for this first one, we know that the hyperbolic sine of h of negative x is equal to the negative sine of h of x. Or the hyperbolic sine of h, sorry. I'm still getting used to saying hyperbolic. Anyway, so this just shows us that the hyperbolic sine of h is odd, just like sine, interestingly enough. And then you'll also see here that the hyperbolic cosine of negative x is equal to the hyperbolic sine, or the hyperbolic cosine of x. Similarly, to the unit circle, we have an identity here that cosine of the hyperbolic cosine squared of x minus the hyperbolic sine of x is equal to 1. And 1 minus the hyperbolic tangent squared of x is equal to the hyperbolic secant squared of x. And we are going to show that those are true here in a moment. We also have the hyperbolic sine of a plus b is equal to the hyperbolic of sine of a times by the hyperbolic cosine of b plus the hyperbolic cosine of a times by the hyperbolic sine of b. And then finally we have the hyperbolic of cosine of a plus b is equal to the hyperbolic cosine of a times by the hyperbolic cosine of b plus the hyperbolic sine of a times by the hyperbolic sine of b. And those are just written out for us there. So we want to prove that the hyperbolic cosine squared of h of x minus the hyperbolic sine of h of x is equal to 1. So the way that we're going to do this is we are going to say that cosine of h, alright, so we are going to say cosine of h squared of x minus sine of h squared of x is equal to 1. We are going to sub in what we know these values to be. So we know that cosine of h is going to be e to the x plus e to the negative x over 2. Square that minus e to the x minus e to the negative x all over 2. And that is equal to 1. Okay, now what do we do? Well, we're going to expand this out a little here. So we are going to do... Okay, so we have 2, or e to the x times by e to the x, so it's just e to the 2x, plus twice the product of these two, e to the x times by e to the negative x is just 1, times that by 2, we get 2, plus e to the negative x squared is just e to the negative 2x, all over 2, minus, alright, so now we are minusing, well, this expression here is squared, so we get e to the 2x minus the product of these, so minus 2, plus the second one squared, which is going to give us e to the negative 2x all over 2. And that is equal to 1. Now I'm going to multiply through this expression times by 2. So we get e to the 2x plus 2 plus e to the negative 2x minus e to the e to the 2x plus 2 minus e to the negative 2x is equal to 2. So we see that there's several cancellations here. So I forgot to actually apply the square to the denominator here, so it's over 4. So we're multiplying through by 4, rather. And what we see is we get 4 is equal to 4, as thus the left side is always equal to the right side. So we have proven that this cosine of h minus sine of h squared of x is equal to 1. And if we really want to prove that, we can divide both sides by 4, and we get 1 is equal to 1, since I originally multiplied by 4. Now what we can do is we can just take our original expression here, which is cosine of h squared, or the hyperbolic sine of h squared, minus the hyperbolic sine of h, or the hyperbolic sine of x, sorry, sine of h squared of x is equal to 1. And now what we're going to do is we're going to divide through by the hyperbolic cosine of h squared. And we can now show that the hyperbolic cosine squared of h divided by the hyperbolic cosine of x is just 1. The hyperbolic sine of x divided by the hyperbolic cosine of x is just tangent, so that will be the hyperbolic tangent squared. Alright. And finally, 1 over the hyperbolic cosine is just secant, the hyperbolic secant, so we get an answer of secant, the hyperbolic secant of x squared. Alright, and we've proven both expressions. So next up, we have some derivatives of these trig functions. So the derivative of the hyperbolic sine of x is cosine of x. The derivative of the hyperbolic cosine of x is the hyperbolic sine of x. The derivative of the hyperbolic tangent is the hyperbolic secant squared of x. The derivative of the hyperbolic cosecant of x is equal to negative cosecant, negative cosecant, the hyperbolic cosecant of x, times by the hyperbolic cotangent of x. The derivative of the hyperbolic secant of x is equal to the hyperbolic secant of x times by the hyperbolic tangent of x, and the derivative of the hyperbolic cotangent of x is equal to the negative hyperbolic cosecant squared of x. So now what we're going to do here is we're just going to solve these expressions, or find the following expressions. So we have the derivative with respect to t of the hyperbolic sine of h of ln of t, and we have the derivative with respect to t of the natural log of sine, the hyperbolic sine of t. So, to start out, we know the derivative of the hyperbolic sine is cosine. So we get cosine, or the hyperbolic cosine, of the natural log of t times by the derivative of the inside function, which is just 1 over t. So we get an answer of the hyperbolic cosine of the natural log of t divided by t. And there we go. For the second one, we're going to have to do a bit of simplification afterwards, I can tell. But we are going to get an answer. Well, the derivative of the hyperbolic of the natural log of the hyperbolic sine of t is going to be 1 over the hyperbolic sine of t times by the derivative of the inside, which is going to be the hyperbolic cosine of t. So we're just left with the hyperbolic tangent of t as our answer. And that actually worked out really nicely, didn't it? Alright. So now we are left with some hyperbolic trig functions. Or the inverse hyperbolic trig functions.
Is that you?
So, for these inverse hyperbolic functions, there's several definitions of them. We have the hyperbolic sine inverse of x is equal to the natural log of x plus the square root of x squared plus 1. Then for the hyperbolic cosine inverse of x, it's the natural log of x plus the square root of x squared minus 1. And finally, for the hyperbolic tangent inverse of x, we have 1/2 the natural log of 1 plus x over 1 minus x. So, if we want to find the hyperbolic cosine inverse of 1, we just have to plug in 1 to these expressions. So we get the natural log of 1 plus the square root of 1 squared minus 1. And now we just get the natural log of 1, which is equal to 0. Which makes sense if we go back up to our hyperbola. Because this hyperbolic cosine is this x value. So, and if it's 0, it's going to only be 1. If that makes sense. Alright. That's what we're working on here in a moment. For this hyperbolic sine inverse of 1, we get the natural log of 1 plus the square root of 1 plus 1. So we get the natural log of 1 plus the square root of 2 as our answer. And of course, we can't really simplify any more than that. Alright, now time for the derivatives of the inverse hyperbolic functions. So we have the derivative of the, and I'm not going to actually talk about all of these, I'll let you look at them. Take a moment, take them in. And now let's work on my 2 problems that I have for us. So we have the hyperbolic sine inverse of negative 2x. So this is a channel derivative. So we're going to take, so we start with taking, apologies, the derivative of the outside function. So we get 1 over the square root of 1 plus, remember, this isn't an x squared if there's an argument in there. We have to summon the negative 2x, the argument, into it, the u, and then square that, times by the derivative of the inside, which is just negative 2. So we get an answer of negative 2 over the square root of 1 plus 4x squared. as our answer. Alright, moving on to this next problem. We have a bit more complicated of a... Alright, so we take the derivative of the outside function. In this case, it is going to be negative 1 over, well, we have a sine of theta times by the square root of 1 minus sine squared of theta times by the derivative, and I suppose it should be with respect to theta. Sorry. Actually, you know what? We're going to keep that as a dx. Interestingly enough, it does still work. We're just going to have to do an extra chain rule derivative at the very end. So now we're going to take the derivative of sine here. So the derivative of sine, as we know, is cosine of theta. So, and we now also have to take the derivative of theta with respect to x. Kind of cursed, because normally it's like dx with respect to theta, but I digress. You may recognize that this sine 1 minus sine squared, using a trig identity, can be simplified. So, using our cosine squared of x plus sine squared of x is equal to 1, we can see cosine squared of x is equal to 1 minus sine squared of x. And if that is true, we can simplify this expression to be negative cosine of theta divided by sine of theta times by the square root of cosine of theta squared, which gives us negative cosine of theta divided by sine of theta times by the absolute value of cosine of theta as our answer. Some people may try canceling this theta. However, I believe it's forced to not always be positive, so I'm not going to in this case. Alrighty, well, that's all I have for you today. I hope you have a wonderful rest of your evening, and goodbye.